we'll see. We'll see. Yeah, so often people are kind of nervous about category theory, but one of the kind of themes that I want to bring home in the talk is that categories are reasonably ordinary algebraic structures, and the things that you do with categories are actually quite familiar constructions, and that's kind of the whole point of category theory. It's to give you a way of translating familiar constructions into unfamiliar mathematical settings. And I won't actually show you any unfamiliar mathematical settings in this talk because they tend to be scary to look at, right? Which would kind of undermine the idea of making category theory less scary. But I think hopefully what we will do is look at some familiar situations from a strange point of view. Is it everything working? Yeah. Great. I shall just, Ricardo will have to forgive me for moving him out of the way. Okay, great. So I'm going to start with a kind of non-mathematical fable that just sets the scene conceptually. So suppose we have a factory, and this factory receives shipments of scrap wire. So they receive, you know, things like this, right? This is like what they get, okay? And what they output is cake toppers. So that's stuff like this. I mean, obviously, this is supposed to be like a piece of wire, so you have to imagine these are small. And you know, you stick this in a cake with many layers, and the cake doesn't fall down, and it has a lovely heart on the top. So that's what the factory makes. And inspecting the incoming scrap wires and sorting them is a worker. And the worker's job is to say, can I find one of these inside one of these somewhere, right? And on the output side of the factory, we have another worker who examines the box sets of cake toppers that come out, who asks for every model of cake topper that the factory makes, is there one of these in the box set? And here we have an example of a box set that comes out of the factory. And the question is, does it pass quality control? Well, the first worker here, the input guy, is happy and says, yeah, I can find one of these inside this thing, because I can kind of morph this thing into that thing using the processes that are possible inside the factory. Like I can chop it, I can bend it. Maybe they can't remove, you know, really sharp kinks or something like that. Might not be economically worth their while to have the machine to do that. But okay, if I cut that bit off, then there's probably enough wire there that I can bend this into that. But the quality control person on the output side of the factory is not happy, because he says, well, there's the heart-shaped cake topper that's missing in this so-called box set. And we just have that strange piece of wire. So they seem to disagree about which objects are equal to what, and whether you can find one of these in one of these. They seem to have a fundamental disagreement about the world. And of course, they don't really have a disagreement. Instead, each one is considering objects not as like atoms arranged in a shape of a cake topper, but as objects which come with a set of processes that they have in mind. So for the input guy, he's thinking about the processes that are possible in the factory. And the output person is just thinking about, you know, rigid transformations, which is what you expect the customer to do. I mean, if the customer starts bending this, then that's their own fault. On the other hand, if the customer has to bend it in order to get it into a heart shape, then that's not what they want. So they're thinking not of the concrete things, but as these things, as really just the connection points between processes, and it's the processes that they're really thinking about. There are a few things that they do agree about. So one thing they agree about is that this thing definitely occurs in itself. And the other thing they agree about is if you have one thing that occurs in another thing, and this thing occurs in yet another thing, this gives a way in which the little thing occurs in the great big thing. And if they thought about it, they would agree that if you take this trivial way that a thing occurs in itself, and you use this as one of the two inputs to this composition process, then you just get out the other one. So this is an identity element for this composition the way I've described this is now a bit horrible because I've called these like ways in which one thing occurs in another. So we'll call these morphisms. They're ways for the input person, they're ways in which one thing can be morphed into another. And the output person could also use that name, although they don't really do any morphing, they just move stuff around. So this is the part of the structure that they agree on. They have different notions of the processes which can act on objects, but they agree about these kind of algebraic laws about how these processes interact. So that's the end of my non-mathematical fable. Let's take some familiar mathematical objects, but relate them in many different ways. So we're going to take the natural numbers for the objects for all of our examples, and then we're going to think about different kind of ways of transforming natural numbers into others, or of relationships that can hold between natural numbers as the morphisms, and we'll see what we get out. We'll see what kinds of structures we get out. So the first question we're going to ask is, what are the morphisms? So from a natural number m to a natural number n, what are we going to allow for morphisms in our example categories? So we'll have the first category A, going to say that a morphism from m to n is a natural number k such that m plus k equals n. So it's quite a natural idea for how you might transform one natural number into another, or a way of comparing natural numbers. B is going to do something similar. It's going to say a morphism from m to n is a natural number k, such that if you multiply m and k, then you get n. Now we'll have a slightly weirder example. So the category C is going to say that a morphism from m to n is an m tuple, so like a list of m elements, where each element is between 1 and n. And some of you will have probably already seen what that is in disguise, but don't worry about that. And finally, we'll take an m by n matrix over the reals as the morphisms from m to n in the category D. So I hope I'll get some audience participation now. In the category A, how many morphisms are there from the number 2 to the number 3? Yeah.
1.
Yeah, 1. And what about in category B? How many morphisms from the number 2 to the number 3? 0. Yeah. And in category C, how many morphisms are there from 2 to 3? Yeah.
Is it 2?
So we're thinking of lists of length 2 of numbers from 1 to 3.
Also 9.
I think, yeah, I think it is 9. Yeah. Yeah, so it's the it's n to the power m. Yeah, yeah. And then D, it's not fair to ask how many. Why is it not fair to ask how many there are? There are uncountably many matrices over the reals. with dimensions m and n. And I guess you could kind of think of them as being parameterized by a cylinder, right? Because, oh, well, no, from 2 to 3, they're parameterized by something horrible. If it was 1 to 2, they would be parameterized by the points of a cylinder. You don't really need to worry about this remark. It's just, some of you in the 3rd year might actually know what they're parameterized by if you go from 2 to 3. Each one is determined by a choice of 2 vectors, essentially, in 3D, right? So, but there are probably some degenerate cases which come out the same. So you can think about that yourself. So these categories, just like the thing with the wires, they give different answers about, you know, if you like, you could think about this as saying, in what ways does one number occur in another? Category A says that 2 does occur in 3 somewhere, in a unique place, actually. I say place, that's a little bit, you can't really imagine it. Maybe you can imagine it as a place, but maybe you can't. B says that 2 does not occur in 3 anywhere. C says that there are like 9 different number 2s inside the number 3. And D says there's uncountably many, a huge family. So each of these categories, they have the same objects, but they kind of picture these objects very differently. And you could imagine that instead of familiar objects, you had some weird objects with definitions that come from you know, modern maths papers or from computer science papers. And because these objects come with a notion of morphisms, you can kind of ask, instead of trying to digest the scary definition, why don't we instead study the kind of patterns of relationships between these objects given by the morphisms? And that's kind of the idea of how you would study a structure with category theory. But let's go back to something concrete. So the next thing to ask is, so far I've only told you what the morphisms are, but category is an algebraic structure. It has to have this composition operation. So I have to tell you how to compose these morphisms in each case. So in the category A, I compose morphisms by adding them. In B, this won't be a great surprise, compose morphisms by, no, is that, I wonder if that's a mistake. If anyone thinks that's a mistake when I tell you what the identities are, etc., let me know. But I think if P is a witness that n is divisible by m, and Q is a witness that, I don't know, T is divisible by n, then I think the product of these numbers is just the number you need to prove that you know, the number at the end, let's say T is divisible by m. That's the example I intended to write down. If I've made a mistake, it might dawn on you, one of you during the talk. Now for category C, it's going to have to be a bit more complicated. This is the formula. So I didn't say what numbers these were going between, and now I need to know this one. This one, let's just call it m, so it matches this example. So imagine I'm given an m tuple, which is called P. So it has components P1 up to Pm, and I'm given, let's say, an n tuple Q. So that has components Q1 up to Qn. Well, each component of P is a number from 1 to n. So that means given a component of P, which is a number from 1 to n, I can look at the component of Q at that location. Does that make sense? Can everybody see why this is well defined? Why is it that for every pi, Q subscript pi is well defined? Well, it's because every pi is a number from 1 to n, if n is the number in the middle here. And Q is an n tuple, so it has components Q1 up to Qn. So this is definitely well defined. Finally, no prizes for guessing that the operation for the composite operation for D is matrix multiplication. So now I think I've told you the composition. You could have guessed some of these compositions, but I could have always turned around and said, oh no, I actually wanted some other category, because this is an important part of the data of the category is its composition. Just like if I told you the elements of a group, you might be able to guess the operations of the group from the elements, but I could have had some weird operations in mind. On the other hand, now I've told you the compositions, you might be able to work out the identity elements. That is, for every natural number m, there has to be an element which goes from m to m, such that if I compose it with any other morphism, I get back that other morphism. So for category A, what do you think the identity is? You can shout.
0.
0. Yeah, thanks. And for B,
1.
1. I hope I've written the right thing. Yeah. Yes. Now, anyone have an idea what the identity for C looks like? The identity from M to M. I'll let you think about it for a little while I sneakily check my clock. Yeah.
Would it be an M tuple filled with the number M?
No, but that's a nice thought.
Maybe 1 tuple with that number.
Sorry?
Maybe 1 tuple with that number.
It can't be a 1 tuple
Oh, yeah.
because we know it has to be an M tuple.
Yeah. M tuple for what?
The n tuple from 1 to m. Yeah, it's that thing. It's the m tuple from 1 to m. If you think about what this will do, say it's easier to think if I apply a q after it, it takes q1 up to, oh, hang on. Q has to be an m tuple because it has to come out of this m. So if I put this thing before it, it just takes q1 up to qm. And then if q gives me some numbers from 1 to m, then if I look, let's say q1 was 2, I look in the second position of this tuple and I get a 2. So that was a rough argument that both ways round, if you compose this thing with any other morphism of the right kind, it has to have it has to be an m tuple of numbers from oh no, I guess on this side it has to only contain numbers from 1 to m, and to compose on this side it has to be an m tuple of numbers from 1 to something something mysterious. Anyone want to ask about that one? I see a lot of furrowed brows, which is good. You can maybe think about it yourself. And for matrix multiplication, it's the m by m identity matrix. And so you might find this a bit weird that I have an algebraic structure where I'm only allowed to compose morphisms if we call these the source and target. So the target of P is equal to the source of Q, right? I don't get a composition, unlike in a group where I can multiply any 2 elements. I don't get a composition for any 2 morphisms in my category, only when they match. And for some reason, this freaks people out, but everybody in the first year learns matrix multiplication, where a matrix has a number of rows and a number of columns, and I can only multiply 2 matrices. The rows of the first match the columns of the second. So everybody learns very early in their mathematical career an example of a partial algebraic structure where whether you can combine elements is controlled by this kind of check, where each one has a kind of incoming thing and an outgoing thing, and the incoming and outgoing things have to match. Matrices are an example of that. So this is quite familiar, but for some reason, people get freaked out about every example that isn't matrices, and they just use matrices without thinking that this is the same thing that they're afraid of for some reason in every other case. Okay, did I put anything else here? No, okay. So now we know a little bit about what these categories are like. We're going to look at one or two categorical constructions. So what's the point of putting morphisms between natural numbers? It's to think of the natural numbers as mathematical objects which get into certain relationships with each other. And different choices of morphisms give the natural numbers a kind of different nature as mathematical objects. And now what we want to do is to do some constructions inside these categories to pick out elements which have certain relationships to certain other elements and study them. So that was all a bit abstract, but again, in the integers, you can ask what's the multiplicative inverse of this element. In a group, you can ask for the conjugate of an element. And so in a category, you might also want to say, given some elements, can I find another element which stands in some interesting and important relationship to the given ones? So the construction that we'll look at is called the product. And it goes like this. Given two objects of the category M and N, which in our examples are just numbers, you have to supply this object, which we call M times N. But of course, this times, the meaning of this times symbol is being defined by this definition of the product. It might not be the ordinary multiplication, which is familiar from abstract algebra, that I might redefine. I might define some operation, which is not the familiar thing. And so what should the relationship be between the product of M and N and the two elements M and N? Well, the product has to have two morphisms, one into M, which I'll call pi1, and one into N, which I'll call pi2. And it has to be special amongst all things like that, things which have a morphism into M and a morphism into N. And so what makes it special? Well, given another one, so there's one called J, which has morphisms J1 and J2 into M and N. This one, the product, is the special one, and it's special because given any other, there has to be a unique morphism, which we usually call mu, into the product, such that if I compose mu with pi1, I get J1, and if I compose mu with pi2, I get J2. So this is sort of saying that the product is like the best one, because if I have any other one, there's a way of kind of encoding it in terms of the product. And mu here would kind of give the way of encoding all the data of J, J1, and J2 get encoded in this morphism from J into the product. So let's think about what this would mean for the first of the categories. So in the first category, a morphism from one number to another is a natural number that I add to the first to get the second. So, and these are natural numbers, right? So addition on natural numbers is particularly simple in various ways. So can you tell me anything? So if I pick two natural numbers, M and N, can you tell me anything about M cross N?
It should be smaller than 2.
Yeah, it has to be smaller, right? Because there has to be a number that I can add to it to get M, that I can add to it to get N. And because these are all natural numbers, I don't have any negative numbers. So it's got to be smaller. And of course, any J has got to be smaller than both. So in this category, the existence of this pair of morphisms just tells us that the object that they come out of is smaller than both the objects that they go into. So that's the property that M cross N, but also any J have. They're smaller than both M and N. So now let's think about what the mu is saying. The mu says that any J which is smaller than both M and N stands in a particular relationship to M cross N. What's that? what does the mu say about J and M cross N here? Yeah.
That J is smaller than M times N? Or do we...
Yeah, exactly. J is smaller than M cross N. So M cross N is something smaller than both M and N. And when we say smaller, of course, these morphisms could be 0. So it's less than or equal to. It's less than or equal to both M and N, but it's the biggest such thing. It's the biggest number, which is less than or equal to both M and N. Does anyone have a familiar, a cute name for that number? The minimum, exactly. So in the category A, the product is the minimum of M and N, and pi1, we won't bother listing both of the projections. Pi1 you could think of as being 0 if M is the smaller of the two, and otherwise it's M minus N. So what about in the category B? Anybody, we can go back to the diagram as well if you want. So who wants to go back and look at the diagram? Yeah, okay, we have one person. Let's and I'll tell you the definitions of the category. Well, let's think through this in the same way. So we have M and N, and we know that M cross N, there's a number I can multiply it with to get M, and a number I can multiply it with to get N. So can we rephrase that as, okay, I think you were slightly faster.
But basically, this is the notion of divisibility, right?
Yeah, right.
So if M times N divides M, but every other divisor of M divides M times N, then it means that this is the greatest common divisor?
Yeah, thanks. So here we have the greatest common divisor of M and N. Anybody want to ask why that is, or do you kind of see the analogy with the minimum example? Now, there's something in these two examples that I never bothered to check. I kind of told you what pi1 is. You can kind of often picture what mu has to be like. But why did I never bother to check whether mu followed by pi1 was actually equal to j1 in these examples? It's worth maybe looking what is pi1 in this example. Well, you could write it as m over the greatest common divisor of m and n. I could have actually written this morphism like that as well. I could have written this as m minus the minimum of m and n. It's just that in that case, it's pretty easy to write down a more concrete definition. So in the first two examples, what's the maximum number of morphisms I can possibly have between any two numbers? Let's think about the addition example. The minimum is 0. Well, okay, in the addition example, let's think about the multiplication example. It's a bit easier. So in the multiplication example, I know I can have 0 morphisms because there's the case of 2 and 3 where there's no morphism from one to the other. Now, in the case of 2 and 4, how many morphisms do I have? One, yeah. Can you think of an example where I get more than one morphism? So a morphism in this category is a natural number, so that when I multiply the source, the input number, by it, I get the output number, the target. It's actually not possible, right? Because you can divide by the source. Now, division isn't always defined in the natural numbers, but it is if you happen to know that there is a natural number k such that m times k equals n. If there were two k and k prime, you would have mk equals n and mk prime equals n. And you could divide by the n, the m, and you would find that k equals k prime. Okay. So that's how we could fill that in. Anybody want to guess what number is going to be here? M cross n for this strange thing. This thing looks very weird, doesn't it? But does anybody have a more familiar way of describing this strange tuple construction? You might realize when you see the product. Does anyone want to have a guess for which number is the product in this category?
This is a guess, but is it an M tuple filled with M?
But that's, you're thinking about the morphism pi1. But just what sort of, how big do you think the object is, the product? Like what number do you think it is? This is a sneaky one because the product is the ordinary product of natural numbers in this case. So now you know what the product is. Can you think about how to define pi1? And pi1 has to be an m cross n tuple. So it has to have m cross n elements. And it has to output numbers from 1 to m. This will be really hard, I think, in the time I'm giving you, but I'll let you think about it a little bit because I think that will be kind of enjoyable, hopefully. Maybe I'll give you a kind of hint. You want it to be a bit like n copies of the identity from m to m, sort of on top of each other, although there's no, I mean, in a tuple, there's no on top of each other, but maybe that was too much of a hint, actually. Yeah.
Yeah, so then would it be like 1, 2, 3 to m, then 1, 2, 3 to m, n times?
Yeah. So again, you should really check these things if you kind of, you know, don't believe them or something. And you shouldn't believe them, right, as mathematicians. You should think this guy comes in from the computer science department. He says all this stuff about natural numbers. It could all be false. In this category, we actually have to check this composition thing. So I'm not going to do it because, you know, it'll just be quite long and tedious, but hopefully it's true. If you find out it isn't, send me an email and maybe let me know what the actual projection is. This is definitely the size of the projection. And I'll tell you why, because this category is the category of finite sets. You can think of an object as this category as the set of numbers from 1 to m. And this tuple thing is just a function, because what does a function from 1 to m to the set 1 to n look like? Well, I have to say where it sends all of the numbers from 1, 2, 3 up to m. So it's just given by a list of m numbers from 1 to n. So this is actually the category of finite sets, or to put it better, it's the category whose objects are like finite prefixes of the natural numbers there. The sets 1 to n. So this is the ordinary Cartesian product of sets, except that we're naming these sets by their size. So the Cartesian product has size m cross n. And now, maybe this analogy with the Cartesian product will help those of you who know something about linear algebra to guess what the product is in this category where the morphisms are matrices. But again, I think this is quite challenging, especially in this situation at the end of a talk. If I gave you more time to contemplate it. But does anyone know, so what would you call the vector space whose vectors are pairs of vectors, one from one space and one from the other? And I just do everything component-wise. The addition and the scaling is just component-wise. Yeah.
Product space?
Yeah, I mean, as a category theorist, I would call this the Cartesian product. But in linear algebra, they usually call it something else. I think. I mean, it's a weird foreign land for me, linear algebra, but maybe you were taught by somebody too educated and they called this the Cartesian product like a category theorist would. Or do you know the dimension of this vector space? Because here, this category whose morphisms are matrices, it's really treating each natural number as a vector space whose dimension is that natural number. And do you know the dimension of the vector space that I get if I take the Cartesian product of the underlying vectors? If you actually think about what one of those vectors is, like how many components does it have? It has all of the components of the vector from the first space, and then all of the components of the vector from the second space. So how many components in total? N plus n, yeah. So in this category, the product of m and n is m plus n. Pi 1 looks like this, where this is like an m by m identity matrix and a bunch of zeros down here. And I think they call this the direct sum vector space people. But again, if you're maybe this terminology is going out of favor, because if you call this the Cartesian product, then it kind of agrees with its name in all the other categories. So often in algebra, you have a historical name for these constructions, and they're all different because they were all studied by different people. But as time goes by, people are often using the category theoretic name for these constructions, because it's kind of bad to think of them as being given by the concrete recipe, which has this traditional name, and better to think of them in terms of this uniform construction that, by the way, not every category has these constructions, just like, you know, not every ring has, there are things that not every ring has, right? But you can always ask in any category, do you have a Cartesian product? And in a particular case, you can answer yes. And then the point is that you can have similar intuitions about all of these, right? You could take a proof about this one. Let's say you love linear algebra and you hate greatest common divisors. You could take a proof about this one. And as long as that proof is only really about how morphisms out of this thing interact with morphisms out of other vector spaces, then I can translate it to, you know, GCD, which maybe I don't like or something. So you can take intuitions from one area and transform them to the other, as long as what you prove isn't about the concrete recipe for how you construct these things, but about the kind of the algebra of how the morphisms interact with each other. And okay, all these are kind of familiar examples, but you can imagine if you have some weird structure coming from computer science or physics or from research level mathematics, it's comforting to say, what's the product of these weird structures? It'll be given by some horrifying recipe, but its behavior in some ways will be just like the behavior of these operations on natural numbers if you take the right notion of morphisms. Okay, now everything in category theory has a dual concept where I turn all of the arrows around. So products have a dual concept called coproducts. The coproduct of m and n is m plus n, and it has morphisms going into it from m and n. And every other thing which has morphisms going into it from m and n has a unique morphism from the coproduct into it. So it's just the product, but everything has been turned around. Now let's do a kind of quick fire round where you have to just guess the coproduct in each of these categories. So please shout. Well, I guess for COVID reasons, you have to kind of loudly, but without too much movement of the lungs, communicate. So in the category A, what do you think the coproduct is?
Maximum.
Maximum, yeah. In the category B, what do you think the coproduct is?
Least common multiple.
Yeah, least common multiple. In the category C, what do you think the coproduct is?
Divided by n.
No, that's a good answer, but So if you think of these as sets, finite sets, I'm looking for a set in which both of the two input finite sets kind of map into. And the question is, I guess, why don't you get the maximum? Because you might be thinking, well, any other set which they both map into, the maximum has to map into. But you'll fall afoul of these triangles because there'll be some kind of arbitrary choices. That's something maybe you should just think about. So if you think about this diagram, which I have finite sets, why does the maximum not work? The set whose size is the maximum of these two sizes. Why doesn't it work?
Because then there is no single defined new that goes into J. Because I have more elements, I can map whatever I want.
Yeah, I think it is related to. So there are two things that could go wrong. Either mu could fail to exist, or it could fail to be uniquely defined. And I think it's the unique definition which fails. So you have to think of this as a set in which these two sets map in such a way as there are no arbitrary choices about where to map each element of the inputs. Anyone want to guess what such a thing is like? This is a good exercise, actually. I hadn't realized how much intuition was contained in this example. Yeah, so if I take the maximum of the two things, then there are some kind of arbitrary choices because I'm going to have to map an element of the set 1 to n and an element of the set 1 to m to the same thing, unless one of them is 0. If they're non-zero and I take the maximum, then there's going to be some coincidences where an element of this one is sent to the same thing as an element of that one for no good reason. So how big does this thing have to be so that I can map these two things in with no coincidences where nothing from here ends up set equal to something from there when I map them in?
M plus n.
M plus n, yeah. So this one is m plus n. And now, is anybody brave enough to guess what's the coproduct in this category? I don't think you'll be able to calculate this one. That's a very nice suggestion, m times n. Well, you're wrong, it's plus again. Thank you, goodbye. So this is a really weird situation. The product and the coproduct in this category are the same. Such a thing is called a byproduct, which I'm not going to go into, but it turns out that this actually kind of every category with a byproduct has a composition rule for its morphisms, which kind of looks like matrix multiplication, especially if every object is just a byproduct. If you have one object, so in the natural numbers, you have the number 1, and every natural number is a sum of a bunch of 1s. And if you're in a category where you have a special object and a byproduct, and every other object is just a byproduct of many copies of the special object, then it turns out that you can kind of write your morphisms as matrices, and matrix composition will be exactly the composition. So seeing that takes a lot of work. I don't propose we do that in 30 seconds. But this weird situation is one of the kind of signs that you have a category of matrix-like morphisms going on. So again, you might be in an unfamiliar situation where the morphisms are described by some terrifying construction, but you notice this product-coproduct coincidence, and it tells you that the morphisms are kind of matrixy, and some of your intuitions about matrices will hold for them. So that's the end of my talk. I thought I would leave you on this disturbing observation. Any questions? No, you understood everything. Now you're going to go out and apply category theory. Whenever you see a factory which makes cake toppers, you'll say there is category theory.
What's the result of the consequence of having the same product and co-product in category?
Oh yeah, so if the product and the co-product are the same, maybe I can. Is there anybody? Yeah. Oh,
if you bring the mouse to the top.
Oh yeah. Oh, there are actually.
It's just this
Oh, okay, yeah, fine. So in that case, if there's any chalk, I bet there's no chalk, is there? No. Okay, so maybe I'll have to use the visualizer. So if we can switch on the visualizer in less than the amount of time it takes to finish the.
There are no chalk and you have to draw.
Oh. I'm not sure that there are drawers. Yeah. That's exactly what I. No, that's what I wanted to do. But I guess I have to switch this on. Which is generally. Oh. Yeah, so switch that on, switch that to that, and then on Zoom. Oh, Zoom already knows. No, Zoom, that's probably because the screen is probably showing the visualizer. So in that case, if I switch back to the PC, and then in Zoom, I do a new share, and I share that. Oh, well, hi. That's nice for the recording, I guess. Share screen.
No, it is that one. But you have to switch cameras. Yeah. So
Right.
you need to share this one.
Yeah. Do you know which one it is?
Oh, you can switch one.
Oh, of course. Right. Yeah. Thanks. Okay. There's the visualizer. So is that you'll have to make do with my notepad. So let's suppose I have a byproduct in my category, which people usually write as a plus in a circle. So they write that for a byproduct. Maybe I'll move this over. I might get more of my voice. Now, suppose we have two objects, A and B, and we have some morphism F from A to B. Well, okay, let's suppose both of these are byproducts of something. So A is going to be a byproduct of A and A1. B is a byproduct of B and B, A1 and A2, and B is a byproduct of B1 and B2. Now, I have to make sure I remember this because I'm kind of doing this off the top of my head. But because I know this one, because it's a byproduct, it's a co-product. So I have these two injections from A1 and A2. And I know that this one is a product. I hope I'm doing this the right way around. So I get two projections onto B1 and B2. And now I get these four composites, right? I can do I1F pi1, I1F pi2, I2F pi1, and I2F pi 2. And I have to remember exactly how you arrange them so that you get, I guess as long as you pick one dimension for the i's and one dimension for the pi's, then I should be okay. So I think maybe if I put like, so there's pi 2 after f, that's too small, isn't it?
You need to move the sheet up.
Oh, thank you very much. Yeah, so there's pi, oh, well, let's say pi 1 after f after iota 1, or I'll just read that as I1 to save some breath. Pi 1 after f after iota 2. I only needed it to be wide and not tall. Pi 2 after f after I1, and pi 2 after f after I2. So I get these 4 composites. And now what I want to convince you of is that f is the unique thing from this byproduct to this byproduct, which has these 4 composites. So f is kind of uniquely identified by this data. And we know since B1 byproduct B2 is the product, f is uniquely identified by these 2 composites, pi 1 after f and pi 2 after f. So now we just want to make sure that these 2 are uniquely identified by their composites with the injections. So here we have B. I should have brought a different color, shouldn't I? But we have B, which now satisfies the property of the co-product of A1 and A2 because it has a map I1 followed by pi 1 after f from A1, and it has a map I2 followed by pi 1 after f from A2. And so it kind of, I like to call this an imposter. It's an imposter for the co-product because the co-product is somebody with maps from A1 and A2 into it. And B1 has these composites. So that means there must be a unique map. There must be a unique map from this byproduct into B1, which has these 2 composites as its well, such that so the point is I get these 2 composites like pi 1 after f after I1, and I get the second one, and then this map here pi 1 after f must be the unique thing which gives me these composites because of the uniqueness property of the co-product. And similarly, this one has to be the unique thing which gives me its 2 composites by a similar argument where now B2 becomes something that looks like the co-product. So F is at least uniquely determined by this data. And then if you just go through the same exercise for a composite, you take an F and a G and you split it into these components. And then you ask, what are the components of the composite? You'll find that the pattern that you get is essentially the rule for matrix multiplication. But I guess there won't be, instead of addition and, there won't be addition and stuff in it. There'll be some kind of like encoded version. But the kind of matching up that you have to do, where you match some pieces with each other, I guess composition is going to be like the multiplication. But I don't know what the addition is going to be. So yeah, maybe you have to be a bit suspicious about my claim because I don't know what the addition is going to be. So well, try it and see what you get. And you should be able to write the composite in terms of these data. But if you don't believe me that it looks like matrix multiplication, then maybe you need your category to be a little bit nicer for that pattern to be really apparent. But the same kind of pairing up of different components will happen. And then you can imagine, okay, this looked like a special situation because I had an object that I could decompose in the input and an object that I could decompose in the output. But if there's a special object which everything decomposes into just a big string of these byproducts together, then the number of times that special thing occurs in the byproduct is like the dimension of the objects. And then you really do get something that looks like matrix multiplication. This thing you get here will be more like if you have two like block matrices where you don't know what the actual elements are, but you know someone has split up the matrix into blocks, and you write down the composition. Then I think you'll get something similar to the rule you get here. Okay, so I kind of remembered this. Thanks for asking. Anybody else? I know somebody had to disappear at, oh, that person has gone. No, it's you, isn't it? Don't you have to give a talk? Oh, he's gone. Okay, that's fine. I'm not keeping anyone then. So any other questions? Yeah.
Like, where are the most interesting applications of category theory in your experience?
Yeah, I guess so. That's a question with kind of two parts. So because there's two different kinds of applications in maths. One is applying a piece of pure maths to other areas of pure maths. And then category theory was originally developed for the needs of algebraic topology. And still, I think algebraic topological ideas drive the forefront of research in category theory in a certain direction. So that research direction, which I think started in the 30s, is still going. So the idea is there that you have certain constructions on topological spaces, but you get the feeling that the spaces are just a particular model of the idea. And the idea that you're actually trying to study doesn't have to do with the details, the geometric details of the space, but it has to do with some algebraic data or combinatorial data. And then category theory is very useful for finding algebraic or combinatorial objects which stand in the same relations to each other as your original spaces stood, and therefore which let you express this idea in terms of the objects that you feel it should be expressed in terms of. So that's one kind of application which drives category theory forwards in a particular direction. What you get there is, instead of considering just a set of morphisms between two objects. So we saw two situations in today's talk. One is that we had two categories where there either is or there isn't a morphism between two objects. And we had two categories where there could be a whole set of morphisms between two objects. Now you could ask, could I have another structure there? Like, I could have a group and then I could multiply, if I had two parallel morphisms, I could multiply them together. Or I could have a space. I could think, maybe morphisms can be close or far from each other. So between two objects, I could have a whole space of morphisms. You could ask, what if between two objects, I had a category of morphisms? So I had morphisms between the morphisms. And obviously, once you count 1, 2, you want to go to infinity. So you can say, well, is there a thing called an infinity category, which has the property that between any two of its objects, there's an infinity category of morphisms? And it turns out that things like that are what model the modern needs of the needs of modern algebraic topologists. And so that's one direction which rapidly leads to the forefront of research in category theory and is motivated by applications in algebraic topology, but also to some extent applications in physics, in the very mathematical end of theoretical physics. Because in physics, you probably have some intuition, either from genuine study or, like me, from pop science articles in the press, that in physics, you often have too many descriptions of the world, right? You have lots of descriptions of the physically the same situation. Like a very common example is something like, when you describe I don't know, because I don't know anything about physics, but if you had like a Tesla coil in here or something, and you went around with a voltmeter, sticking the two ends in the air, you would get some numbers out. And those numbers are physical because the voltmeter measures them. But you might imagine that to every point in space, you could assign a number called the voltage, such that the number the voltmeter measures is the difference between voltages. But no device can measure the voltage. It can only measure the voltage differences. So you would have a kind of constant, like a constant of integration. As long as you add the same constant to every voltage in space, you get the same answer out. Now, there are many more sophisticated situations where you have a whole family of mathematical objects which describe the same physical situation. And things like infinity categories, it turns out, are very good at describing how to work with these things. Because you might say, well, okay, to get a theory, I can just take the quotient. I can take all these things which describe the same physical situation, and I take the quotient. The problem is the quotient often has a horrible mathematical structure. So like your original space of states, where there are many states that describe the same situation, has some algebra that you can do on it, or it's geometrically nice. When you take the quotient, the resulting thing is geometrically horrible and has no algebraic structure. So then you're like, okay, well, maybe mathematicians will just study the unquotiented thing. And then we'll always remember that when you get to the physical world, you have to treat, whole families of states as being really the same. But the theory of infinity categories is developed so that you can kind of have your cake and eat it too, where the infinity categories kind of encode all of these kind of physical sameness things in such a way that you work with the original nice objects, but everything you do is kind of forced to respect the equivalence relation, which gives them physical meaning, as long as it's all written in terms of webs of relations in the category and not in terms of concrete recipes. So that was a long-winded way of getting there. The second kind of applications, so there's kind of a new field called applied category theory, which tries to find uses for category theory in applications in the more traditional sense, like out there in the world. You can think of this as having a very long history in computer science. In computer science, category theory happens to be an excellent model for certain things in the theory of programming languages. And so when programmers write a program, they want to kind of organize this program nicely so that you can reason about it and maintain it, etc. And it turns out that the structures that programmers kind of discovered to organize programs essentially turn out to be category theoretic constructions. And viewing them that way, again, it removes the arbitrary recipe aspect, and it makes the reasoning more clear. And it means you can do things like move to a different model. So instead of thinking about what the programs are doing all the time, you say, well, I have these nice mathematical objects which have the same constructions on them, so I could think about those instead. So this was a very long-running application of category theory to the design of programming languages and to some extent the design of programs. But people are interested in more general kind of processes. There are lots of processes in the world with like, you can do them in series and parallel, and maybe they have feedback and stuff like this. If you look in different branches of science, from say parts of quantum mechanics to things in biology, like studies of how populations of rabbits and foxes interact with each other. People often talk, instead of talking about the detailed models, they draw kind of diagrams of processes which happen together, or one after the other, or have feedback loops, etc. And these diagrams, even though the different sciences look different, these diagrams all look kind of the same, which describe these causal processes. And so there's a bunch of work ongoing right now in finding good category theoretic models which give a kind of abstract meaning to these diagrams, independent of the particular sciences where they occur, so that you could have, there are some universal reasoning principles, and maybe there are some special ones which come from those particular areas, but you could kind of separate the universal reasoning principles for these kinds of causal diagrams. And that could become just a mathematical subject. And it would simplify these papers. There's a really funny paper in some medical journal where the person essentially reinvents one of the famous approximations to the integral. They don't realize that they want to do integration. So they are like, oh, we have to find the area under this graph. We chop it up into rectangles and we add them all together. And this got published just as a method in some strange medical area. And of course, you look at that and you say, what a waste of effort, right? Like, this is just a famous approximation to integration. You could have just put your function into any one of a bunch of software and got a much better approximation. And so the idea with this applied category theory is sort of the same. Instead of all these people who draw these causal diagrams reinventing the same idea over and over again in every field, you take the ideas which are all in common and invent them all once. And then people are left just studying what's really special about each area. Sorry, that was kind of a novel as a response to your question, but what time is it now? Am I no more white hairs? Okay, so wasn't that long. I guess at the rate I'm going, I've got time for one more. Okay, let's call it. Oh yeah, okay.
Actually, no one has one. So I wanted to ask you about like more foundational level of category theory. Like, for example, I think we can have like a categorical set, right? But then we get to the same point of the Russell paradox, like what are they contained in, right? And we just say, well, is there this thing called objects, and what really is that? Because we don't want to get into the Russell paradox again, right? So what are we storing this data in?
Yeah, so you kind of can't escape the Russell paradox. The Russell paradox is that you can't have a set of all sets, right? So originally you wanted to found mathematics on set theory, and you were hoping that every collection of mathematical objects would form a set, and then set theory would do everything because of that. The problem is the collection of sets can't be a set, otherwise you get inconsistencies. And there are a bunch of standard tricks to deal with that, like you imagine there's an infinite hierarchy of flavors of sets, and all the sets of one flavor form a set of a higher flavor in the hierarchy. And those tricks are always needed at some point, I think, in a foundational enterprise. I don't think anybody knows a way of escaping them. But you don't have to found category theory on sets. So you can say that a category is a set of objects, which might be one of these sets from high in the hierarchy, right? And between every two objects is a set of morphisms. That's the usual way of thinking about it. But you don't have to do that. Just like set theory can be axiomatized in first order logic, you can just write down the axioms of a category in first order logic. And then you can write down a certain number of axioms which make this category behave like the category of sets. So you really can start with category theory instead of starting with set theory and describing categories. You can start, so that way, you start with first order logic, you axiomatize the notion of a set in first order logic, and then once you have this notion of set, you construct the categories. You can go the other way around. You can start with first order logic, you can write down the axioms of a category, and then you can add axioms until you get the category of sets. And some people even try to go further by axiomatizing enough constructions on categories that you can construct a category of sets. This is maybe a little bit old-fashioned, I think. So at least you have a choice in the foundations. But category theoretically, there's something more satisfying to do, which is to start with a different foundational system. So in the set theoretic way of doing things, you start with first order logic, which you imagine is kind of not mathematics. It's just about how to reason. And then you add axioms, which you think of as basic facts about the mathematical world. And your reasoning system, first order logic, then tells you everything about mathematics from these axioms. That was the kind of dream. Of course, there's Russell's paradox, Gödel's incompleteness theorem, etc. happens to you. But still, that's the kind of default way of thinking. But it turns out, I'm not sure how well I'm going to be able to describe this idea, but you can start from a different foundation, which is called type theory. And in type theory, you don't separate your sets, which in type theory are called types. You don't separate those from logical propositions. So let me share this thing again. So you could make a category whose objects are logical propositions like claims about the world, and the morphisms are implications or proofs from one proposition to another. And in the category whose morphisms are implications, the product is like the conjunction of the two propositions because it implies both of them, and it doesn't imply anything else, right? I mean, there are lots of things that imply both of them, but the product is unique because it implies both of them efficiently. It doesn't imply any extra weird stuff. The co-product is the disjunction, the or of the two propositions. In the category of proofs, the product is definitely the conjunction, and the disjunction is something, I mean, the co-product, I would have to think very, very hard. So if you think category theoretically, logic is just kind of another example of a category with a certain behavior. So it's not very natural to say that you begin with logic and you add axioms to get set theory. Instead, you axiomatize a category from the inside. Okay, instead of saying I have a collection of objects, in first order logic you have variables and you have quantifiers and stuff, right? And it's as if you're saying, instead of I'm saying I have variables, and then I add some axioms to say that these variables behave like sets. I take a system where I have some variables, but I don't have any quantifiers or conjunction or implication. I just have a bunch of variables. And then I add some constructions which become like the and, or, and the quantifier. But instead of thinking about these as logical constructions, I think about them as category theoretic constructions. So instead of saying for every two propositions, I have something called P and Q, you just say for every two variables, I have this thing, variable one cross variable two, and it has this certain behavior, which you describe by giving something that looks like a logical inference rule. But the logical inference rule kind of encodes this kind of situation. And I don't think I'm doing that great description of this. So if you Google type theory, well, that's kind of the idea. The point is that the logic and the objects that the logic talks about kind of come into being at the same time. Because instead of having separate logical constructions and then using those to describe constructions on sets, you just say I have these things which have these constructions on them, and I use them both to make logical claims and to describe the things that these claims are about. And that's a more satisfying way of starting from nothing, constructing logic and sets at the same time based on their category theoretic behavior, and then getting going. But you won't dodge Russell's paradox. At some point, you will have to say that there's these things called small sets, and then there's large sets of type 1, 2, 3, 4, 5. I don't think you need up to 5. I mean, probably the needs of all of mathematics. Concrete. When I say concrete mathematics, I don't mean like sand going through a sieve or something. I mean, modern algebraic geometry, you probably only need 2 set theoretic levels above the base. Only for research in set theory itself do you need to go to very high levels. And it's believed that even for modern algebraic geometry, it becomes easy to organize if you let yourself have 2 levels of sets above the basic ones. But you can kind of get rid of them. If you want to use, say, a paper of Grothendieck to actually calculate, how many solutions a polynomial has, well, the paper will be organized assuming that you have a couple of levels of sets above the basic, the small sets. But if you work through a particular example, you actually don't need them. You only need them to organize the theory of all the examples. So for concrete stuff, you can kind of practically avoid those tricks. Anyway, yeah, that's that. Yeah. And now I think you're tired. The CO2 level inside my mask is reaching the critical critical limit at which thought is no longer possible. And so I'll thank the organizers very much again for having me. Thank you all for listening to me and humoring me. And hopefully I'll see you around. I've been very busy this semester, but if I was less busy, I would go to seminars upstairs. So you might see me in the building, and then you can maybe accost me and say, hey, that thing you said about matrices. It turns out I checked it and it goes wrong. So anyway, hopefully I'll see you soon. Thank you. Thanks.